Hello everyone, welcome to this video series on database management system. So in this video we are going to look at functional dependencies. Okay, so first of all let's see what is a functional dependency. So you can say a functional dependency or an FD is a kind of integrity constraint which can be thought of as a generalized concept of key. Okay, so all of you know what is an integrity constraint, right? So they specify some kind of rule that the data in a table should follow. Okay, then what is the rule that is implied by a functional dependency, right? So this is the definition of a functional dependency, right? Okay, so let's see. So if you take a relation R, that is a table R which is having set of attributes, that is two sets x and y. Okay, then we say that a functional dependency from x to y holds for any instance small r of the relation capital R, if and only if when t1 dot x is equal to t2 dot x, then t1 dot y equal to t2 dot y. So here t1 and t2 are tuples. Okay, so t1 and t2 are tuples. Tuples means rows in a table. Okay, so when do we say that there is a functional dependency from x to y? Only when t1 dot x equal to t2 dot x, then t1 dot y should be equal to t2 dot y. So this is the definition of a functional dependency. So don't worry, I will show you an example and I will explain this definition. So this is the example. So let's go back to the definition. So here they are saying there is a relation R. Okay, so this is the relation R. So this table is R. Okay, which has 4 columns A, B, C, D, right? And there are attribute sets x and y. Okay, so I am taking this set of attributes as x and this one as y. So x is containing A and B attributes and y is having C. Okay, then if it is like that, we can say that there is a functional dependency x to y. That means there is a functional dependency AB to C. When can we say that? When if t1 dot x equal to t2 dot x, so let's say this is t1 and this row is t2. Okay, so t1 dot x means this one, a1 b1. Okay, equal to t2 dot x means this one. So they are equal, right? a1 b1 is equal to a1 b1. So if that is the case, what should happen? Then t1 dot y should be equal to t2 dot y. So t1 dot y means this should be equal to t2 dot y means this. So all the things are satisfied. So we can say that there is a functional dependency from AB to C. Okay, I hope the example is clear, right? Okay, so once again go through the definition and look at this example and see whether this functional dependency is right or not. Okay, it is right because it is following the definition. When a1 b1 is equal to a1 b1 in 2 rows, then this one c1 should be equal to c1. Okay, right. Now are there any more functional dependencies? So can you tell me? So take some, pause the video and take some time and come up with any more functional dependencies. Okay, right. So there are 2 more FDs from AB to D and A to D. Okay, so first let's see this one, AB to D. That means from this to this. So here you have 2 sets of values which are same, and here also you have D to D2 same, right? So you can say that there is a functional dependency from AB to D. Now what about this one, A1 to D1? So you can see in 3 rows you have the same value, and here also in the corresponding 3 rows under D you have D2 same value. So you can say that this functional dependency holds. Okay, so from this example we got 3 functional dependencies. Okay, are there still any more functional dependencies? Can you tell me? Okay, so take this as exercise and give the answer. You can comment below the video what are the further FDs you found, right? Okay, now if you are given a set of FDs, let's say the set of FDs you are already given are A to B, okay, and let's say you are also given another functional dependency B to C. Okay, so if you are given, so this is the set F, capital F. So if you are given a set of FDs, then you can say a functional dependency small f, for example, let's say A to C. So this is small f. You can say that this small f functional dependency is implied by this capital F only when this holds true for a relation instance where this entire set of FDs holds true. Okay, then you can say that this functional dependency is implied by this set of functional dependencies. So that is this thing. Okay, then how to find the set of all FDs which are implied by the set F? That thing will be called as closure of F. Okay, so if you see this A to B and B to C, let's say this is the set F which is already given. Okay, so this set of FDs F is already given. So from these FDs, how do you find which other functional dependencies are implied? Okay, that thing will be called as closure of F, which is denoted by F plus. Okay, so by using these two FDs, you are coming up with new FDs, that you are finding some more FDs which are implied by this set. That thing will be called as closure of F. Okay, by the way, I forgot to tell one more point. So let's say there is a functional dependency A to B. Okay, in a functional dependency, what do you find on left hand side and right hand side? On both left hand side and right hand side, you will find set of attributes. Okay, okay, so here A is set of attributes and B is set of attributes. They can be one attribute or more attributes, both on left hand side or right hand side. Okay, and how do you read this arrow B means? You will say, you can read it as A derives B. Okay, A derives B, or you can say B is functionally dependent on A. Okay, so you will read it like this: A derives B, B is functionally dependent on A. Okay, right. Now, so how do you find F closure? That means closure of F. How do you find? Right, now we will see. So how do you find the closure set of FDs means? We will use something called Armstrong's axioms. So there are 3 rules which are proposed by Armstrong. We call them as Armstrong's axioms, which are used to find the closure set of functional dependencies. Okay, so first rule is reflexivity. So reflexivity says that if y is subset of x, then you can write x derives y. Okay, I am telling again, if the attribute set y is subset of attribute set x, then you can write the functional dependency x derives y. So if you use reflexivity property and you have a relation, let's say ABC, so you have a table R with 3 attributes ABC. By using reflexivity, you can write these functional dependencies: A to A, B to B, and C to C. Okay, I wrote all these three FDs based on this reflexivity principle because A is a subset of itself, right? B is subset of itself and C is subset of itself. So you can write like this: A to A, B to B, and C to C. And second axiom is augmentation. So if you already have a functional dependency x derives y, then for any attribute set z, you can write it as like this: xz derives yz. Okay, fine. And last one is transitivity axiom. So I think all of you are familiar with this from mathematics. If x derives y and there is y derives z, so from this we can infer that x derives z. Okay, x to y, y to z, then we can write x to z. So these are the three Armstrong's axioms. Along with this, we have two additional things. One is union and another one is decomposition. So the union rule says that if there is an FD x derives y and there is another FD x derives z, then you can combine them as x derives yz. Okay, we are just combining the right hand sides, x derives yz. And last rule is decomposition. So decomposition means separating. Okay, so if you have FD x derives y to z, yz, then you can decompose them as x to y and x to z. Okay, so this is like an opposite of union, right? Okay, and here we are defining something called as trivial functional dependency. So what is a trivial functional dependency? If you take a functional dependency where RHS contains only attributes that also appear in LHS, then that is called as trivial FD. So can you think of examples for trivial FDs based on this definition? So these things are trivial FDs: A to A, B to B, okay, C to C. These are trivial FDs because the RHS things are available on LHS. Both are same, right? And you can have trivial FDs like this also: A, B to A, okay, A, B to B. These are also trivial FDs because the RHS is a part of LHS. Okay, right. So what can you say here? Whatever FDs you are getting using the reflexivity principle, they are all trivial FDs. Okay, generally whenever you are finding the closure set of FDs, you don't consider the trivial FDs, you will ignore them. Okay, fine. Now let's see an example. So the given set of FDs are A derives B and B derives C. So this set is given to you. This set of FDs is given to you, and they're asking us to find F closure or closure of F, which is represented with F plus. Okay, then you can apply the Armstrong axiom, which is transitivity rule, and if A to B and there is B to C, then you can say there is an FD A to C. Okay, so F closure contains this one, and now this one. So how did you get this one? By applying transitivity rule. Okay, so along with these three, this and this, now we are applying augmentation rule. So you remember augmentation rule, right? This one. Okay, so by applying this rule, so you can take this A derives B and you can add the another attribute C. Okay, similarly you can take this B derives C and you can write A. Similarly you can take this and you can add B. AB derives AC. That is how you got these three. Okay, and of course you can use the reflexivity rule and you can write all the trivial FDs: A to A, B to B, C to C, etc. And the set of all these FDs is called closure of F or F plus. Okay, I hope you understood. If you have any doubts on this, you can comment below the video. Right. And next one is attribute closure. Okay, previously we have seen FD closure. Now you are seeing only attribute closure. So when do you use attribute closure is whenever you are asked to find whether this FD is part of a set of FDs or not. Okay, so you will be given a set F of FDs, and they are also giving a new FD, this one, and they are asking us to find whether this will be a part of this or not. Okay, in that case you will find the attribute closure of the left hand side, the attribute closure of X, that is called as X plus. Understood why we are discussing this attribute closure concept? Okay, now how do you define this attribute closure? So you can see here, attribute closure is set of attributes A such that X derives A, that can be inferred using Armstrong's axioms. Okay, so don't worry, I will show you the example, you will understand it very easily. Right, now how do you find this thing attribute closure? By using Armstrong's axioms. So there is a small algorithm for this, we will see the algorithm now. Okay, so what are we trying to find? We are trying to find attribute closure of an attribute X. That means we are trying to find X plus. Okay, right. Now initialize the closure with X. That means if you are finding A, if you are finding A plus, first of all include that attribute itself, A. That is this step, closure equal to X. So since I am finding A plus, I am including A. Okay, then there's a loop here. So what is the loop doing? Until when does the loop repeat? The loop repeats until there is no change. So what change they are talking about? They're talking about there is no change in this set. That means if you are not able to add any more attributes to this set, that is when you stop this process. So what is the process? Now if there is an FD of the form U derives V, for example, let's say there is an FD like A to A derives B. Now this is U and this is V. If there is an FD like U derives V, then what they are trying to do? They are doing and also they are saying that there is a condition here. If there is a functional dependency like this where U is a subset of the closure, so U means A and A is a subset of closure, so this condition is satisfied, right? Then what are they doing? They are doing closure equal to closure union V. So what is V here? V, they are adding V to the closure. That means you are adding V. Okay, and you are again going to repeat the loop. For example, there is one more function dependency B to C, then again you will apply this. This will become U, this will become V, and C will be added here. That's all. Since there are no more FDs, we will stop here. So this will not change again, right? And we will stop. So the closure of A plus is ABC based on this given set of FDs. So let's see the example finally. So this is what I have told you previously. So the thing is, they are giving you a set F which contains this and this FD, A to B and B to C. Now if you want to find closure of A, how will you find? First include A itself in the closure. Then is there any FD which is starting with A? Yes, there is FD A to B. So add this B here. And now check for B. Is there any FD with B? Yes, there is. So add this right hand side here. So now is there any FD which begins with C? No, there is no FD. So we will stop here. Okay. Now find the attribute closure of B plus. So write B itself here. Now see if there is any FD starting with B. Yes, there is. So add C here. So is there any FD with C? No. So stop. Similarly for C plus, add C itself. And is there any FD starting with C? No. So stop the process, that's all. So this is how you find attribute closures. Okay, now how is this helpful means, for example, you are given this set of FDs A to B, B to C, you are already given them. Okay, now they are asking to find whether A to C belongs to this set or not. Is this FD implied by this set or not? How can you say? Okay, so this is what I was discussing here. Okay, we can check whether a given FD belongs to a set of FDs or not by finding attribute closure of X. Okay, so here X is this according to that notation. Okay, so find the attribute closure of A. So it is already given here, and I already shown you how to do this, right? Now, does this include this right hand side? Yes. A closure contains C. So you can say that this FD is implied by this FD set. Okay. So that's all. So in this video we have seen what is a functional dependency, how to find closure of a set of functional dependencies, and also at the end you have seen how to find attribute closure. So this topic is very important to understand normalization process and also decomposition process. So I request you to please go through the video again and be comfortable with all these topics. Okay, so please like the video and also subscribe to my channel for latest notifications. And if you have any doubts, you can comment below the video. Thank you.